Hello. We're going to see if I can get a quick video in before my lab meeting this morning. And then hopefully they're doing yard work outside and hopefully that won't be too loud as they come by with mowers over and over and over again. I'd love to chase them off, but um, it doesn't seem like that's going to be an option. I don't want to seem unreasonable with them. Also, let's see. Um, Lots of folks have been asking about when the exams are. And so the first exam is going to be on October 8th. And then the second exam should be on November 12th. I'll give you approximately 60 to 75 minutes to complete 30 to 40 multiple choice questions. Anyone who has logged disability or student services is also free to take the exam at a testing center. But I also know that if you would prefer that, just let me know and I will give an unlimited number of copies of the exams to the student center. Additional things about exams that you might want to know include that the multiple choice, 75 minutes, they'll be timed, they'll be available online probably all day, but I'll only be available to answer questions during the specified time for the class. So I'll pop on to Zoom, I'll have I'll be available to answer questions in real time, and that will be helpful, I think, in taking the exam to have that added clarification. But hypothetically, you could take the exam before that time or afterward. It's just I won't be available to answer questions at that time, and I'll see about making sure that there's a randomized presentation of questions between individuals so that we don't have like landline parties where everyone's like hanging out, like answering questions at the same time and, producing a giant cheating network. Evidently, that's been an issue in some other classes over the summer, and a bunch of people ended up getting in big trouble over that. So just try not to do that. I'm not going to try to abuse you these exams. These exams will be challenging. They will verify whether or not you know what's going on in this class and whether or not you've been studying. But it's not designed to bludgeon you to death. That being said, be prepared, make note cards, study those note cards, take notes, watch all these lectures, watch them twice, re-listen to them, do whatever you need, just familiarize yourself with this content and be conversational about it. So we're gonna try to cover the first component of the social network lecture, probably over the course of the next 15 or so minutes. I wanna make this a short lecture because the last one was long, so we'll see how I do. So what we'll go over in class or over this unit, we'll talk about what social networks are, what their form and function and general terminology describing them, the kinds of questions that you can address with them, what they're supposed to capture about animal societies. Then we'll talk about various kinds of statistics that you can extract from these social networks to describe social features about individuals and then whole collectives as well. So you can describe individual nodes, where you are positioned relative to your social landscape and highly descriptive terms, but also you can say this network of individuals has certain properties that is different from this aggregative network of individuals. So the neat thing about social networks is that they can tell you something about what an individual's position is relative to its social landscape. It can tell you about the little clique level, so like a bunch of individuals that are like friends or have common affiliations, and then it can say at a broad scale, this total social network of all interacting individuals, what are its features like, and then you can compare those across wildly different taxa. It's hard to interpret what those things would mean, but it does give you a lot of things that you can test. God, I'm so sorry. I have some fun neighbors where I'm at right now. Anyway, so some like drag racing outside. Anyway, so then we'll talk about whether or not the social landscapes that individuals organize themselves into are chaotic, or whether or not they are deterministic. If we know traits about the individual constituents that are going to form a network, can we predict what that network is going to look like? Or is it just like gobbledygook? Like there might be determinative processes, but they're just so nuanced and particular based on circumstances around these individuals that they're very difficult to predict what the combined social network would look like. et cetera, et cetera. So determinism versus chaos versus complete randomness in the generation of social networks and individuals' positions within them. So the question becomes, if you could just simulate your life again, your Facebook life, your Instagram life, your Snapchat life, your life with your friends, your life with your family, would it all happen the same way over and over and over based on individual starting traits? Or were there particulars about the landscape when these things were developing, the social landscape when these things were developing, that make it very difficult to infer how a social network will be composed at the end? Or is it completely random? And the fact that there's basically no relationship between individual traits or circumstances in the generation of these networks, which is like the totally random notion. We'll talk about multi-layer networks, dynamic social networks versus static social networks, and then we'll talk about social networks and multi-level selection, which is a topic that we covered. The former is a topic that we covered in a previous lecture. Social networks. Here's an example of a social network. Social networks have nodes. That's these little circles here. And in social networks, usually these nodes are individuals. So here's an individual that has only interacted for however long we've been observing this group. This individual has only interacted with this individual. This individual is another unique individual, and it's connected socially to several other individuals. These lines that connect them, those lines are called edges. So we have nodes in blue and edges in white. So this blue individual has many more connections than this first blue individual. So this one you could say is maybe more socially integrated. So counting the number of connections that an individual node has is called its degree, like degrees Celsius or degrees Fahrenheit or various degrees of punishment, etc. All right, so you have these edges. So you can count them, but these edges also have differences in thickness, don't they? So these are called weighted edges. So there can be unweighted edges, which just mean that all of them would have the same thickness, or you can have weighted edges where individuals that interact over and over and over during your observation period get a thicker and thicker line. So this connection between these two individuals is very well established. Is this an affiliative interaction? Is it an aggressive series of interactions? Is it allo grooming, or is it, this network doesn't tell you what these edges are meant to signify, but what it does tell you is that whatever social relationship is going on here, good or bad or whatever in between, they're interacting a lot, much more so than this individual and that individual. So already encapsulated within this network, we can see that we can identify individuals that are highly socially integrated. We can see who their most common partners are. So, and instead of just like counting this individual is more social than individual A is more social than individual B, or vice versa, here you can say who they're social with, where they reside in a social landscape with much greater specificity and statistical aptitude than you would have without social networks. So it is no shock that with the advent of higher levels of computational methods in behavioral ecology and evolutionary biology, social networks were borrowed from other disciplines like computer science to begin to ask questions about social evolution. You can, in aggregate, you can say things like, okay, how many cliques are there in this group? There's one clique here, right? This little triad of individuals that are interacting on the regular. Who's the most socially connected individual? It's this individual here. Who could be individuals that are riding off their coattails, that have lots of other connections to them? So if this individual becomes ascendant and these edges have some sort of affiliative bond, a social positive bond, animal friendships, you could say these other individuals that are highly connected might have a coattail effect that have a positive impact on their social and or reproductive lives with the ascendance of this individual to some sort of social power. So already in a relatively simple network of just 7 individuals, we can infer a great deal more about this social group than we would have been able to get from just counting up the number of interactions each individual had. Social networks can be depicted, the same social network can be depicted with many different constellations. This social network right here is the exact same information as this social network. I just moved it all around. So, you know, this clique is still here. These two individuals still have very tight bonds. These edges all have the same weight. So you will see different orientations of nodes. Most commonly, you'll see things like these that that allow you to see as many of the nodes as possible, as many of the edges as possible. The other common constellation that you'll observe is you'll see all the nodes in a giant ring, and then you'll see just connections between them, and that's like a little like a dream catcher type looking thing. I'm sure it has a proper name. I don't remember its proper name, but anyway, so it has with that you can see who's connected to who in sort of gestalt patterns. So in small networks like these, it's very easy to trace all the edges and all the nodes and have the same kind of information, right? This is an outlandish notion. I don't know why anyone would depict a network like this one, but at least you can see all the edges, you can see all the nodes. As you add more nodes to the network, you could have dozens of nodes or hundreds of nodes, thousands. I mean, on something like Facebook, which does track your social network explicitly and statistically, you can have hundreds of millions of individuals that are connected to each other. And so how do you depict that visually? Big challenge. So most of our social networks that we deal with behavioral ecology are relatively small, and if they are larger, they can be depicted in little rings and things that get the general pattern of social interactions across. Thankfully, you don't have to really visualize it. Computers are very good at figuring out social network statistics from even very elaborate kinds of networks that are not easily digestible to the human eye or brain. So hooray for computer science. All right, so first we'll go over some basics of form of function of social networks. I covered a little bit of that already, but we'll revisit that ground. Why not? Anything worth saying, anything worth doing is worth overdoing. All right, so here's a social network of hyenas, spotted hyenas, and we have when there's a low prey availability set of conditions and a high prey availability set of conditions. And already you see a couple of things here. One, these nodes are color coordinated with different values, right? So maybe these are different social groups of these hyena that have metagroup dynamics. So they're relatively stable clique social groups that interact and exchange individuals with each other relatively frequently. And then you might have isolated individuals. But these cliques are now color coordinated to draw your eye to them. Although in some cases, the depiction of these social networks, these different color coordinations or numbers will have other node attributes, that's a special term, a node attribute, attached to them. It could be sex, it could be reproductive status, it could be how many pups they've had, it could be how many years you've been observing them, or whatever. Something about those individuals can be encoded into these nodes, and then you can give that to a computer, and it can account for these node attributes when trying to figure out, are females more connected than males? Are dominant females more socially connected than subordinate females? Are solitary individuals more likely to be in better or worse condition in terms of percent body fat? Things like this. They allow you to test an innumerable number of correlations. And so one of the foibles of social networks is that you had better have very clear hypotheses when you start doing your analysis of social networks, because if you don't, you can basically test hundreds or thousands of hypotheses, and then some of them, just by chance, you're going to get beautiful patterns, and that's just going to happen by chance alone. So you have to be really careful at articulating what the hypotheses are that you're going to address using your social networks to begin with, and then evaluate those with hypothesis testing, and then you can go exploring later on, but it's easy to go very, very far from the edge of the woods statistically with these networks, and that can lead to erroneous conclusions and interpreting patterns that actually are just chance patterns. Anyway, so the nice thing about these group attributes is that they can tell you the group structure overall. So you get a pattern of that there are highly connected cliques, and then there are sort of like less connected cliques, and then there are more or less solitary individuals like here in green. And you can get a sense of how those things change through time, like the level of connections between the cliques of the purple group and the like a rust orange colored group here become much more highly connected during high prey availability sets of conditions. And it's a more diffuse set of interactions during low prey availability. So you kind of get that gestalt because you can just see that web work of those nodes become denser under the high prey availability set of conditions. You can also look at individual traits of these nodes, these individual attributes, reproductive status, sex, personality, whatever. Anything you can measure about an individual, you can encode into these nodes. And then you know individuals' relationships are social roles. Are they lone wolves? Are they mostly isolated lone wolves, figurative lone wolves, hyenas, or are they highly connected? This is lone wolves. If these things are aggressive interaction networks, you might be able to try to infer which of these individuals are dominant or which individuals are subordinate, et cetera, et cetera. Form and function. Nodes, these circles, but they could be stars or whatever, denote individuals in social networks. Edges devote some kind of social interactions. Nodes can be encoded with traits or attributes, sex, personality, reproductive status, social status, whatever, age, anything you want, anything you can think of measuring. And then edges can be weighted. They can be thin for sets of interactions that are not all that common. They can be thick for interactions that are observed very regularly. And then they can be directed or undirected. Directed means there's an individual that originates the social interaction. It's the antagonist, or it's the individual starting that affiliative social bond, the positive social bond. It initiates the grooming event. And if you have observations that allow you to figure out who started that interaction, that allows you to have an arrow that points from one individual to another. This individual initiated an interaction towards this individual. This individual regularly initiates an interaction towards this individual, and only rarely does it return the favor. So hypothetically, if this is a social grooming network, this would be a highly asymmetrical relationship where this individual is exhibiting a lot of affiliative positive interactions towards this individual, and it's obtaining very little directly in return. An asymmetrical relationship. If you wondered what that would look like graphically from social networks, this is what it looks like. This is where I would make a joke about re-examining all of your social relationships and looking for things like this, and then redetermining whether or not those are interactions that are worth your time. Anyway, so edges can be directed or undirected. There can be an instigator and receiver, or they can be undirected, which will just have connections here. And we don't know who started those interactions. We just know that they happen. And it can sometimes be very difficult to infer who starts an interaction based on just like watching things. Like all of a sudden, both monkeys just bristle and attack each other. You're like, oh, well, Jesus, we don't know who started this interaction. But sometimes it's very obvious. Individual A walks over to individual B and starts picking through his hair and eating lice. Very obvious. Individual B was just sitting there. Individual A got up, walked over, initiated the interaction. So directed edges provide you with more information. Weighted edges provide you with more information, more node attributes provide you with more information, and then that can allow you to ask more and more sophisticated questions. Are individuals in low body condition more likely to have asymmetrical social relationships? Are individuals that are low ranking or are high ranking individuals likely to be the recipient, a positive recipient of asymmetrical social relationships? People sort of, other individuals buttering them up or giving them resources, sharing food when they very rarely do it in exchange. Just a hypothesis. All right, so that original network from before, I've recoded it here. Now there's males and females, right? And so now you can ask yourself, like, okay, are males or females more or less socially connected? You can use each of these nodes. You can calculate the number of edges that they have connecting them. You can include weighting information, and you can examine whether or not males or females have greater or reduced social connectedness. It's not obvious here that that would be so. There are two males that are relatively isolated, two females that are relatively isolated, and then one highly integrated male and two highly integrated females. It's hard to say. And I still haven't articulated what these edges mean. The network that describes aggressive interactions could be totally unlike a social network that describes affiliative interactions. And only rarely are we now able to take social networks that describe different kinds of relationships between individuals, who grooms who attacks who shares food with who shares space or cohabitates in a tree at night with the other individual, and then put them all together and try to analyze them all together. Because presumably, who you fight with, and then who you have close social bonds with, or who you cohabitate with or share food with, would not be socially independent, right? Like, it's unlikely that I'm going to beat the crap out of some other monkey, and then the monkey's going to be, we're going to have a great relationship 5 minutes later. They're probably going to be linked to each other. But up until very recently, in the last few years, do we actually try to account for all of those properties simultaneously in something called a multi-layer network? On average, we're just looking at one set of interactions We create one of these networks for some amount of time. We might watch the animals for a few days, a few weeks, a few months, maybe a year, and then we try to create one of these networks. So in practice, you can have a lot of different kinds of social networks. So here's a picture of a bunch of my Facebook friends that showed up here, and you can see who I'm connected with, how regularly I interact with them, and there are algorithms that things like Facebook use based on my social network structure to determine whose posts I should see, whose posts I'm not gonna like, whose posts I am gonna like, what's gonna keep me online looking at their ads for longer. Yeah, they're taking a huge amount of data. So really the real pioneers about the methods that underlie what we're using in behavioral ecology now have been computer scientists and entrepreneurs for decades. So examples of things that you might use to create a social network might be something like who's grooming who attacks who is cohabitating in a tree at night with who is banding up with who during conflicts, things like this. And how do you acquire this information? You can use direct observation. You just Jane Goodall at Dian Fossey, wander around outside and just stare at these monkeys for years of your life. And you're going to figure out who's who and be able to recognize individuals and create all these social networks. But the problem with that approach is that you can only watch a monkey for so much of your life, right? Like they're going to be away sometimes. You're going to eventually go away. So what you really want to be able to do is you want to be able to just sit in your apartment someplace like in Toronto or Hamilton and have something else collecting the data for you. Thank God in the modern age, we don't have to go around and spend our lives in Uganda staring at chimpanzees. We can just track them. We can track them automatically. So for example, we might have tiny little rice-sized RFID trackers. Disney World uses these for like fast passes in your little like wrist. You like touch this thing to the sensor and it lets you know whether or not you as an individual actually have a fast pass for this ride. If you tap if you tap your wristband against this this reader and you're not supposed to be on this ride, it recognizes who you are because inside of your tiny little wristband is a non-energetic, it does not have a battery, a tiny little RFID reader. Or RFID tag. And when it goes close to a reader, that can have a set level of specificity within a few inches or a few feet or a few meters. If an RFID tag goes by that reader, you can say that individual was there. That's that individual. It was near this reader. So that's useful because if you set up a network of these readers all over a forest, and you're tracking something like this blue tit here that has a tiny little pit tag, an RFID tag on the inside of it, inserted beneath the skin, you can say this individual showed up at this feeder at this time, this feeder at this time, this feeder at this time, this feeder at this time. And in addition to tracking that individual's movements, you can track who arrived shortly before and after it. And using these co-occurrence matrices, like individual showed up here, and then 2 seconds later, another individual showed up, you can begin to try to infer whether or not they're in a social group together. They certainly appear to be moving together if they arrive in close proximity to each other, to feeders around the forest, over and over and over again. Hooray for pit tags. They're cheap, they're small, they are broadly available, they're not energetic, they don't have a battery associated with them. Problem, RFID readers do require energy, they do require a battery that has to be changed regularly, and they only have a certain distance that they can sense individuals as they move by, right? They have to pass that barcode near one of those readers. And without it, we don't know what they're doing in the meantime. So you basically have to bait things like your readers. So like we think that these crabs are going to use these coral heads. So we put all of our RFID readers in these coral heads. If the crabs decide to go nowhere near the coral heads at all, and they start living in the sand, we're just screwed. We don't know where they went. And then same thing with these bluebirds, like if we, these blue tits here. So if we give these things RFID tags and we put RFID readers out at all these stations with food, we're not going to know where these birds are unless they're next to one of these readers. And when they're not next to one of these readers, whatever we're doing, we can't infer. These two birds that show up together over and over and over, we begin to create a hypothesis that they have a close social bond. But the reality is that they might be hating each other the instant that they leave, attacking each other violently, blooding each other up, giving each other death threats, being passive aggressive with each other. We would have no idea. So hooray for RFID readers and pit tags, but it leaves a lot in the dark, and you have to try to create some cutoff of like, if they occur within 6 seconds, they're friends. They occur within 4 seconds of each other, they're friends. What about if they're 20 minutes apart? What if they're 5 minutes apart? Are they not friends? Are they in the same social group? You don't know. You have to just sort of like create a boundary that makes sense, a cutoff, and then try to apply it in the same way. GPS towers, hooray, GPS towers. These are much better. You basically set up a series of GPS towers that can sense the GPS monitors on the animals that you've put monitors on, like neck collars or wrist collars or things like this. And you can triangulate in the position of those animals. So if we have a bunch of baboons with necklaces on that have GPS monitors on them, and they move around our towers, we can sense where individuals are relative to each other, spatially explicitly, all of the time, as long as they remain within our network of towers. We can also do that with things like satellites, but then the resolution is lower. The spatial resolution on the Earth's surface is lower with satellites. It's stronger with the towers, but then the animals have to stay around your set of towers, and you have to have many towers to triangulate in and figure out where these animals actually are relative to each other. One of the other bugaboos about this is that those GPS collars, they break a lot. They have to automatically come off the animal at some point after a few months or a few years sometimes, and they have to have a battery with them as well. And if the battery dies, well, the monitor is not working any longer, and they're expensive. The GPS monitors are super expensive. You have to trank the animals, get these giant collars on them. They end up pulling them off. They sometimes get them latched on the fences and plants and whatnot. So there are a lot of issues with these, but none of these methods are perfect. But the cool thing about the GPS tracking is that you can watch, as long as they're in that space, you can see who's next to who all the time. They don't have to just show up at your feeder. We know what they're doing when they're at the feeder, when they're away from the feeder, et cetera, et cetera, et cetera. So hooray for GPS monitoring. Rather than get into the common issues, I'm going to stop it there because it's been 26 minutes and I promised a shorter lecture today, and I've got lab meeting in just a few seconds. So I'm going to cut this here, and then we'll resume social network statistics next week, which will be probably the whole week on social network statistics. All right, take it easy, guys. Start studying for the exam. Don't postpone it. Start it now. Please, please, please. I want you to knock it out of the park, and then I want to be embarrassed by how well you guys did on the exam. All right? Please. The opposite would make me quite sad. All right, so stop sharing, and we're going to stop this.